We start with definition of alternating series. An infinite series is an alternating series if it is of the form -1 to n plus 1 and from 1 to infinity, which is a1 minus a2 plus a3 minus a4 plus and so on, or of the form -1 to n and from 1 to infinity, which is -a1 plus a2 minus a3 plus a4 and so on. So alternating series basically means that the sign of the terms of alternates between plus and minus. So here we assume that n are positive for all n. A couple of examples. Say we have -1 to n and from 1 to infinity. That is -1 plus 1, -1 plus 1, -1 and so on. That's the first example of alternating series. Another example, and from 1 to infinity, -1 to n plus 1 divided by n. So that's 1 over 1 minus 1 over 2 plus 1/3 minus 1/4 plus and so on. That is so-called alternating harmonic series. Next theorem is alternating series test, which will help us to determine if given alternating series is convergent. So we start the alternating series. -1 to n plus 1 and from 1 to infinity, be an alternating series. Here I will assume that n is bigger than 0 for all n. Okay. Now, if the given series satisfies of following two conditions. So the first condition will say that the limit of an when n is approaching infinity equals to 0. The second condition will say that an is bigger than an plus 1, bigger or equal. In other words, an are decreasing sequence. If these two conditions are met, then conclusion is that our original alternating series is convergent. I start with a small comment. If the first condition is not met, if the limit of n is not equals to 0 when n is approaching infinity, that also means that limit of -1 to n plus 1 n is not equals to 0 when n is approaching infinity. Therefore, by divergence test, we conclude that -1 to n plus 1 n infinite series is divergent. So if the first condition is not met, then the series can be divergent. So that's the first comment about the first condition. That's why we must have a first condition for a series to be convergent. Now let's get an idea why do we get that alternating series test. Firstly, let's look at our series. -1 to n plus 1 an, and from 1 to infinity, that is a1 minus a2 plus a3 minus a4 plus a5 minus a6 plus and so on. So we're going to look at the even partial sum. So even partial sum we're going to look like a sub 2n. So we start with a1, then subtract a2, and add a3, then subtract a4, and so on, plus an minus 1 minus a sub 2n. If you look at the two consecutive even partial sums, so if I look at the next consecutive even partial sum, so that's 1 before, and we have to add two terms to it. So two terms to it is going to be next term, an plus 1 with plus, and a sub 2n plus 2 with minus. Notice that because we assume that we have terms are decreasing, so when a sub 2n plus 1 is going to be bigger than a sub 2n plus 2, so that expression will be positive. So we conclude that s sub 2n plus 2 is going to be bigger or equal than s sub 2n. So we have sequence of even partial sums is increasing. The first comment which we might make, it's increasing. Now let's have a look at our even partial sum one more time. a1 minus a2 plus a3 minus a4 plus a sub 2n minus 1 minus a sub 2n. And what we're going to be doing is we're going to be collecting second and third term together, fourth and fifth term together, and so on and so on. So what I'm trying to do is I'm trying to write down as s sub 2n as a1 plus negative a2 plus a3 plus negative a4 plus a5 plus negative a2 n minus 2 plus a2 n minus 1 minus a sub 2n. Notice that all the expression in parentheses and the last guy are going to be negative. Because again, we assume that a2 is bigger than a3, a4 is bigger than 5, and so on and so on. So we conclude that s sub 2n is going to be less than a1. Now, if you look at what we got even partial sums are increasing, and we're also bounded. Therefore, we conclude that because they're bounded and increasing, so we conclude that therefore limit as n approaching infinity s of 2n exists and say equals to s. Okay, that's the first. Now recall that to get the infinite sum, we need to take limit of all partial sum, not only even. So now let's look for odd partial sums. Odd partial sum is the even partial sum before it plus one more term, and that's going to be odd term, and odd terms are called positive. If I take now limit of odd partial sum, when n is approaching infinity, I'm going to get limit of s sub 2n plus a sub 2n plus 1 as n approaching infinity. By the first condition with theorem, limit of a term is going to be 0. So we're going to get limit of s sub 2n plus 1 of odd partial sum equals to limit of even partial sum when n is approaching infinity, and we know that is equals to s. Therefore, we conclude that our original alternating series is convergent because all partial sums will converge to S.